Okay, so in this video I will go over the problems from quiz 6. So you can check your work against mine. If you have any questions, please let me know. We have 3 questions. So problem 1, we're working in the ring z5x. So the polynomial ring with z5 coefficients, we want to compute the product 3x squared plus 2 times 3x squared plus 3. So this is just like ordinary polynomial multiplication, except our coefficients are elements of z5. So when we're multiplying numbers and adding numbers, we're doing it all mod 5. So we can kind of think of this in a couple of steps. Let's just do the FOIL on this product first. Let's just do it ordinary multiplication. 3x squared times 3x squared plus outside times outside would be 3x squared times 3. Inside times inside would be 2 times 3x squared. And then last times last would be 2 times 3. So now we have to simplify this. And the way we do it is you combine the powers of x. So we have x to the 4th here. And you multiply the coefficients. So 3 times 3. But it's 3 times 3 mod 5. So 3 times 3 is 9. Mod 5 is 4. So 4x to the 4th. Then we've got 3 times 3 x squared. Again, 3 times 3 mod 5 is 4. Then we have x squared here. 2 times 3 is 6. Mod 5 is 1. And 2 times 3 is 6. Mod 5 is 1. Alright, so we've multiplied the coefficients. Now we look for like terms to combine. Well, all we have that are alike are the x squared terms. So we're going to add those coefficients. Again, mod 5. So 4 plus 1 is 5. Mod 5, that's 0. So I'm left with just 4x to the 4th plus 1 as my answer. So that's our product of these two polynomials within the ring z5x. Okay, so next we have an example where we're doing matrix multiplication within the ring M2 Z5. Okay, so we're multiplying the matrix 3, 4, 1, 2 times the matrix 2, 0, 4, 1. So this is just like ordinary matrix multiplication, except when I get to the multiplication and addition of these numbers, I'm doing it all mod 5 again. So do the same pattern as usual, row times column. So 3, 4 times 2, 4. That's 3 times 2 plus 4 times 4. Then we have 3 times 0 plus 4 times 1. And then 1, 2 times 2, 4 would be 1 times 2 plus 2 times 4. And 1, 2 times 0, 1. Since I have limited space because I wasn't careful here, let me just, well, I can do it, I guess. So we simplify each of these 4 numbers, but the operations are done mod 5. So here I will get 6 plus 16. That's 22. But mod 5, 22 is 2. Then we've got 3 times 0 is 0 plus 4. 0 plus 4 is 4. Mod 5, that's still 4. Then we've got 2 plus 8. That's 10. 10 mod 5 is 0. And we've got 0 plus 2. 2 mod 5 is still 2. So our simplified matrix then is 2, 4, 0, 2. All right. Then our third problem is a proof. It's a simpler version of one of the homework problems. So in this situation, we have two rings, R and S, and these are commutative rings with unity. We want to prove that the units, the set of units of R plus S is the same set as U of R plus U of S. Switch markers, I think. Okay, so going back to our definitions. Cat getting in my way here. Going back to our definitions, recall that U of a ring, a commutative ring with unity, is the set of elements that have inverses. All right, so we're trying to show that these two sets are equal. Sorry, BT. Trying to show these two sets are equal. So we want to show if something is here, then it's also here. And then we want to show if an element is here, it's also in here. So it's like two-directional proof here. Let's do this containment first. So this containment means I start with an element of the left side and I show what's contained in the right side. All right, so let an element be contained here. So if it's a unit of R plus S, that means it's an element of R plus S. So let's write it as an ordered pair. If you're in R plus S, it's an ordered pair. Let this be an element of, you can go. Make up your mind. Let RS be an element of U of R plus S. Okay, what that means then, if it's in U of something, that means it has a multiplicative inverse. So then, there exists, I'll write it RS inverse in R plus S. Okay. Another way of saying this is RS inverse has to be an element of R plus S. So that means it's going to be an ordered pair. I'll call it AB, where A is an element of R and B is an element of S. And if it's the inverse of RS, that means, let's say it like this, and. So where A is an element of R and B is an element of S, and if I multiply the ordered pair RS times AB, I get the unity element of R plus S. But that's the ordered pair 1 sub R comma 1 sub S. That's the unity element of R plus S. So this times this cancels and gives me the unity element, the multiplicative identity. All right, but let's now recall how multiplication works in a direct sum. The way you multiply is you multiply corresponding coordinates. So RA comma SB, that has to equal 1R comma 1S. Right? So out of space, I need to erase some things. Let me keep most of the setup here, including what RS was. But now here, what that says is R times A equals 1R. So therefore, this is continued. R times A equals 1 sub R. And S times B equals 1 sub S. But now what that tells us is R, lowercase r, has an inverse. Because I can find something that when I multiply r times it, I get the identity element. So there's an element that cancels r. So r's an element of u of capital R. It's a unit of the ring R. And likewise, I can find something that cancels little s to give me the unity there. So S is an element of U of capital S. So finally, the combination RS, that's an element of the direct sum U of R plus U of S. Because it's an ordered pair where the first coordinate comes from this set and the second coordinate comes from this set. So that tells us that since we started with something that was in U of R plus S, U of R plus S, we started with something there and we showed it was also here, that tells us that U of R plus S is contained inside of U of R plus U of S. This marker is getting low as well. Okay, so that tells us this side is contained in this side. Now we need to do the other direction, which is going to be very similar, I think. But let me erase. Let's try this color. So now we want to do this direction, where that means we start with something in the right side. So let RS be an element of U of R plus U of S. We need to show it's an element of U of R plus S. All right, but what this means is directly R belongs to U of R, U of capital R, and little s belongs to U of capital S. But what it means to be in U of something means there exists an inverse within that ring. So therefore, there exists R inverse in capital R, and there exists S inverse in capital S. And we understand R times R inverse equals 1R. S times S inverse equals 1 sub S. Okay, but now, if we look at RS, the ordered pair RS times the ordered pair R inverse S inverse, by the definition of multiplication in a direct sum, or multiplication of ordered pairs, I multiply the first coordinates and I multiply the second coordinates. So I get R inverse, comma, S inverse, but that's going to be 1R, comma, 1S. And that tells us, again, let me erase because I'm out of space. That tells us that these two ordered pairs are inverses of each other. So therefore, R inverse S inverse is the inverse of the ordered pair RS. Because if I multiply, if I multiply this times RS, they cancel and give me the unity element. So finally, we've said that R comma S, it has an inverse, which is this, so that means it's an element of the units of R plus S. It's a unit of R plus S. So finally, that's telling us that if we start with something in the sum, U of R plus U of S, it's actually in U of R plus S. So we have that containment. Let me be consistent with the sides. We started with something here. We showed it was here. So we've proven this containment. All right, so that finishes the proof. We showed both containments. Both sides contain the other, so they have to be equal to each other. So I'll finish the proof there. All right, so that concludes the quiz 6. Again, if you have questions or need extra clarifications, send me an email. We can either try to address it through email, or if necessary, I can schedule an individual Zoom appointment to discuss it. But that's it.